Yeah, hi everyone. I'm Songlin from Purdue University, and today I'm going to talk to you about our work on polymorphic reachability types. This is a joint work together with Guannan, Oliver, Yuyan, and Tiark. This work has been accepted to POPL earlier this year, and it's our great pleasure to present it here again in person. Looking at the trend of typed system programming languages, Rust perhaps gets most of the attention. It offers many much desired features, including memory safety, thread safety, and pretty good performance comparable to C. The secret sauce behind Rust is the ownership type system, which tracks how resources, especially memory resources, are used. As a culmination of decades of research on ownership types, Rust has become the most admired programming language voted by programmers, even though it is known to be a challenging one. Still, Rust is far from the last language on Earth. Aiming to be a low-level language like C, Rust focuses especially on memory resources. In high-level languages, even though they usually come with automated memory management, tracking the ownership of other resources and their associated capabilities can enable a whole new class of programming paradigms. Following this thread, high-level languages are already motivated to build their own ownership tracking mechanisms. To name a few, Mojo from Modular AI, Swift from Apple, and some OCaml variants from Jane Street. They're all adding some Rust-style ownership types into existing high-level languages. Academic works also reflect this trend. Various substructural type systems have been studied over decades, and recently there's a Haskell extension on linear types, and Scala 3 also introduced capturing types, aiming to ensure safe use of effects. Despite all these proposals on combining functional abstractions and resource tracking mechanisms, there's an inherent tension between Rust's secret sauce and the pervasive sharing style of programming. By Rust secret sauce, we mean its shared editor mutable principle. A resource in Rust can either be shared or be mutable, not both. On the other hand, in higher order functional programming, we use first-class functions everywhere. These functions can capture free variables from their defining environment, and they can even escape from their defining environment. Such capturing gives us a flexible form of implicit sharing, and it gives us the expressive power of functional languages. However, they do make tracking ownership and mutability hard. A concrete example of this tension can be seen in this pair of counters. A reference C can be shared in two closures through which the user can make different mutations. While this is a very common pattern across functional programming and object-oriented programming communities, it clearly violates the Rust principle. Rust is actually right here, since a race condition can occur if the two closures are used in different threads. However, it is too conservative, as serial invocations to these two closures are actually safe. So an ideal type system should be able to return the right of decision to the user so that they can avoid the unsafe cases and continue to use the safe cases. The recently proposed reachability type is such an instance. It allows tracking shared resources at a type level. For example, the CTR counter object marked on the superscript here. Usage code can later use this sharing information to ensure safe and flexible behavior. To quickly wrap up, Rust starts with a strict global invariant and selectively relaxes the usages through borrowing. In contrast, reachability types start with a more liberal sharing foundation, and users can selectively restrict program behaviors on function abstractions. In this work, we build on the top of reachability types and further address the issue of combining them with polymorphism. Specifically, we propose a new notion of freshness, and our new design offers both lightweight and quantified reachability polymorphism. So let's start with some gentle examples. The first key idea is to augment the type system with a qualifier, like Edward has just introduced. So qualifier here in our system is a set of variables that can be reached from the evaluation result of the term E. For example, we can define a variable x bound to a newly allocated reference cell, And the typing of this variable tracks its own variable name, so just x on the qualifier. When we further assign x to y, the type of y will also be qualified with its own variable name. We can later transitively trace its reachability using the typing context. And for primitive resources, such as integers, their qualifier is just an empty set, meaning that they are untracked. Function types also have a qualifier, which is basically the free variables captured by the function, or the function's observable context, we call it. Now the question is, what should the qualifier be for a newly allocated value which does not yet have a name? One possible option is to assign the bottom qualifier since the new reference shares nothing with the environment. However, in this way, we are basically confusing fresh values with untracked values. Either we take fresh values as untracked, which is not sound, or we take untracked values as fresh, which is not precise, and the system becomes non-parametric, like our prior work does. Another option is to assign the top qualifier indicating this value is part of the sharing universe. This is a solution adopted by scalar capturing types, I understand, but the drawback here is that such a top qualifier is also used with all existing values, and thus, additional mechanisms are required to establish the concept of separation. For those curious minds, their degree of separation work is scheduled to give a talk tomorrow. So the new idea of this work is that instead of using either the top or the bottom qualifier, we can designate a special marker for freshness indicating something statically unobservable. In our design, we use this diamond notation for the freshness marker. These unobservable variables or locations may materialize to actual locations during evaluation. So for example, this new ref expression becomes a fresh location after one reduction step. And thus, the freshness marker in its type will be substituted with the new location. A fresh expression can also be bound as a named variable. And importantly, bound variable qualifiers are not subtype of freshness, since they are no longer unobservable, and otherwise we will lose tracking on them. So in this way, we no longer have the conflation of untracked and fresh resources, and it further gives us a parametric treatment of reachability. An important use of this freshness marker is to support both scoped and non-scoped introduction forms of resources. For example, here we have a try combinator which executes a function. This try combinator provides the capability to throw an exception to this function. We do not want this can throw capability to escape, or otherwise exceptions can be thrown outside this trying block, becoming unhandled. So in our type system, this is secured since the qualifier of the can throw capability is C, which is not a subtype of the freshness marker. On the other hand, we can also support non-scoped introduction forms. For example, we can just return a new reference cell from the function body. This works because it is fresh from the beginning. Compared with scalar capturing types, thanks to the expressing power of freshness notion, our system enjoys a more unified treatment as we don't have to differentiate scoped and non-scoped resource types. Other than sharing and aliasing, we're also interested in tracking separation among variables. One natural thought is to retrieve the fact of separation from the typing lattice. But from this example of intersection type, we know that such separation subtyping is hardly derivable syntactically. So what do we do? On the other hand, our newly introduced freshness marker is already a witness for separation, meaning that the fresh notations are separated from all existing variables in the context. While this is a property too strong, here we introduce a generalized version of freshness. We call it observable separation. So by putting a freshness marker on function arguments, we are saying that such arguments are separate from all free variables captured in the function. So let's see a trivial example. This involves the identity function, which carries an empty qualifier, meaning that it captures no free variable. So then that basically means we can pass arbitrary arguments to this function, since everyone is separate from the empty set. Here's a more interesting example where we have two references, C1 and C2. The function addRef captures C1 and tries to mutate it. The formal argument R is declared with the freshness marker, and thus we need to check separation at the time of application. We cannot apply C1 to addRef as the argument, because both the function and the argument can reach C1, and thus C1 is not fresh for the function. The function can accept C2 as an argument, as the reachability intersection is empty. In the above examples, we use the empty intersection of reachability qualifiers to infer the separation of their corresponding locations. This is summed because the underlying invariant enforced by our type system. We can additionally describe the permissible overlap or permissible aliasing pattern on separated arguments by adding variable names into the argument qualifier. So for example here we add C1 into the qualifier of R for this addRef2 function, and thus applying addRef2 with C1 is perfectly okay then. Ensuring separation is very useful in many applications. For example, in the paper, we have shown how to type parallel evaluation combinator, this part that only accepts two sounds with disjoint qualifiers. In this way, we can ensure that non-interference if we run these two sounds in parallel. In this example, the part combinator takes two sounds, one captures C1 and the other captures C2, which is safe. On the top of our design, our calculus offers two forms of precise reachability polymorphism. The first form is lightweight in that it does not require an additional reachability quantifier, and the argument name itself is directly used for abstraction. So for example, in our old friend, the identity function, the resulting qualifier can depend on the input argument x. And there is no loss of precision when applying with any kinds of arguments, since the dependent x will be substituted with the actual reachability. The calculus has also been extended with bounded parametric reachability in the style of system F sub. In this way, we can introduce an additional quantification variable for reachability. For example, the z variable here. This is very useful for expressing polymorphic data structures as well as reachability tunneling, as shown in this pair example down below, where we can build a pair and its component reachability are preserved after projecting the components of this pair. So we have formalized our system with a simply typed version and also a version with F sub style bounded quantification. We have also shown the typability of church encoding of pairs in our F diamond subsystem. We have proven the syntactic soundness of our system using progress and preservation, and our preservation additionally shows that the qualifiers may only grow because of new allocations. One important corollary we have is called preservation of separation, meaning that two separate terms remain separate during evaluation. Our proofs are mechanized in Claude, and there is also a prototype implementation. We call it the diamond language, which you can find in this link and in the tutorial shown here. There's also a series of ongoing work around reachability types. We have been trying to make alternative proofs in logical relations involving more properties, including termination, effect safety, and program equivalence. We're also investigating our design for subtyping and necessary reference, making our calculi more capable of non-trivial structures and more practical. You can also scan the QR codes for on these slides from some of our tech reports and paper drafts. So to conclude, we have proposed polymorphic reachability types with an explicit notion of freshness. It tracks sharing and separation in higher-order generic languages. It provides a foundation to be used in almost any impure functional languages, and it paves the way for integration of reachability types in practical polymorphic languages. Thank you all for listening, and I'm happy to take questions.
Thank you.
Thanks. This is really cool. I'm
So I'm a little bit curious what it looks like in your real implementation, because like all the examples you showed were using superscripts and things I can type in my word processor, but not in source code.
So you're asking
about
the
that?
annotation burden. Okay. So
Yeah, because I assume people have to write these types, right?
yeah. So let me just do some time traveling. Okay. Here you can see that, so basically our typing of variables is very simple. We just type it to the name of the variable itself. So basically here we are doing some lazy things. So we expect you to write no explicit typing when you are, for example, within a function scope. But on function abstractions, we do expect you to state the qualifiers of the argument, since this is the intention, like what kind of argument are you expecting to accept? This is a safety guarantee that we expect developers or programmers to provide, actually. And other than that, we actually have our type system implemented in the bidirectional typing way, so we can do type inference in all other cases, I believe.
Okay, but like at module boundaries, you still have to specify the types, right?
So sorry?
At module boundaries, you would have to specify the types.
Yes, yes.
Yeah, okay. So I wonder, I guess as a follow-up, I mean, your types have sets of variables in them, right?
Sets of variables in them, yes.
So I'm worried, well, should I be worried that these sets can blow up and that we would get really large and unwieldy types?
Very great question. So first of all, I want to ensure you that sets never blow up, because they are all variable names. And we know variable names in a certain program is always finite, right? So this part can be ensured. Yeah, of course, right.
If I have n types and n variables, that could be n squared.
Yeah, good question. But
maybe there's no problem. I'm just curious, right?
Yeah. So basically, we believe that the total sets of all variable names in your scope is the upper bound of the qualifier you can get. This is one part of it. And the other part of it is actually, there are some subtleties in our subtyping design, but we have been proving that our algorithmic version of subtyping is totally sound. And we also have a slightly variant version. We also prove that it is complete. So basically, they are very usable.
Thank you.
Thank you.
Nice. So the number of variables could also be the empty set if you use point-free notation. Can you say something about how would that scale? Does the system work if you use with combinators? It's quite nice to use the variables in the language, but the points, so to speak. But if you have point-free notation, you would like it to be tracking the resources as well, I guess.
What do you mean by point-free notation?
Using combinator style programming, like in Haskell, for instance. Function compositions and so on. So you use.
Yeah, I guess I can try. Let me try to understand if that's the correct question. So currently, our language do support escaping closures. So our way of doing that is, for example, if you have a fresh variable without name and it occurs within a closure, and then we replace its name, we actually use the name of the closure to refer to this free variable, the fresh value, so that there is always something tracked. Yes. I hope this is.
Okay, nice.
Thank you.
Thanks again. This concludes our session. Let's give a round of applause to the speakers.